Okay, so now we've got a bunch of divisibility and factors questions. Most of them are 700 to 800 level. I got a couple that were slightly easier just because I needed to find something that covers everything. Again, I'm doing these blind, so bear with me if there's any that I struggle with a bit, but I think it's useful for you to see sort of how I approach questions, sort of what my thought patterns are. So this first question, a school administrator will assign each student in a group of n students to one of m classrooms. If blah, 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 is it possible to assign each of the n students to one of the m classrooms so that each classroom has the same number of students assigned to it? So a big word soup. Effectively, if we want to have the same number of students in each classroom, then we effectively need that n over m equals integer, right? Because we need, like, n over m is going to be the number of students in each classroom. Obviously, it has to be an integer unless you want to cut students apart. So, okay, that's all we're given in the first bit. And then what are we told? We're told that in statement 1, 3n over m equals integer. And in statement 2, we're told 13n over m equals integer. So what we need to know whether n over m is an integer is, could there be a 3, well, for example, 1, could there be a 3 in m that is sort of being dealt with by this 3 that otherwise wouldn't be dealt with by the n, if that makes sense. Effectively, we need to be able to cancel all the prime factors of m, and so and all of the prime factors of m have to be inside n in order for that to happen. And so if we have 3n over m, then basically what we're worried about is that there's a 3 in m, and therefore that would not be available if we just have n over m. Hopefully that makes sense. So we know that 3 is less than m is less than 13, but that means m could be, for example, 6, in which case there's a chance that there's still a 3 in that m, and so this alone is not going to be sufficient, because we could get a number that is left over, 3 left over. Whereas for 2, we've got the same question. Could there be a 13 in m that would be left over as a result? Well, the answer is actually no, because m is less than 13. And so since 13 is prime, there's no way of actually having a 13 in m. And so, in other words, this must just be 13 times n over m, where this part is an integer. And so that one alone will be enough. And so that's the answer. Okay. M and n are integers such that 6 is less than m is less than n. What is the value of n? Greatest common divisor of m and n is 6. Okay, so in other words, that's highest common factor. So what does that tell us? One tells us, just translating, that m is equal to, well, we must have a 2 and a 3 in m, and we must have a 2 and a 3 in n, and then some other stuff. What is the value of n? Well, okay, and then, well, I mean, that alone really is not enough. I could put anything in n, like effectively, clearly that alone is not enough. I could put, I can make m 2 times 3 times 5 and n, then just add a 7, or I could have added an 11. Like, so that's not enough on its own. So then let's move on to 2. The least common multiple of m and n is 36. So that's more useful, because that means that we already know, well, we don't know much, but we know that effectively they're both bigger than 6. And so what numbers could possibly lead to a least common multiple of 36? Well, let's focus on m. What could that possibly be? Well, it can only be one of the factors of 36. So it could be 9, it could be 12, it could be 18, or it could be 30. No, it couldn't be 36 because n is bigger than m. And so n then could be, it has to be bigger than m. So in this case, it could be 12. In this case, it could be 18. And in this case, it could be 36. So the point being, clearly there's lots of possible values. But if we combine these two ideas together, well, which of these things, if the greatest common divisor of m and n is 6, well, if m is 9, for example, n can only be, well, no, sorry, we need the greatest common divisor to be 6. So, for example, m can only be 12 or 18 because 6 doesn't divide into 9. And if if n was 12, then the greatest common divisor of 12 and 12 would not be 6. And actually, no. So the fact that 9's out means 12's out anyway, because n has to be bigger than m. Ooh, it's a bit of a nasty question, but okay, we're getting there. And so now, well, if m is 12, what can n be? Well, it can only be 18, because if it was 36, then the greatest common divisor would be 12. So it can be 18. We can get that pair. And then if m is 18, can n be 36? Well, the answer is no, because then the greatest common divisor would be 36. So this is the only possible pair, and so both together is enough. Okay, d is a positive integer, and f is the product of the first 30 positive integers. Okay, so f equals 30 factorial. Let's write in a different color. What is the value of d? Okay, 10 to the d is a factor of f. Well, fine. So in other words, that's asking, what we can ask is how many 10s are in 30 factorial. And so using the trick from the notes, we need to know how many 5s are in 30 factorial. And so the trick we do for that, 30 over 5 equals 6. 6 over 5 equals 1, and that's all we're going to get. So that's 7. So d is less than or equal to 7, because we know that 10 to the d is a factor of f, so the most we can have is 7. But that's all it's told us so far. So that alone is not enough. D is greater than 6 on its own is clearly not enough, but both of them together, d is greater than 6 and less than or equal to 7, well then d is equal to 7. So together that's enough. Is n over 18 an integer? So, okay, well, very similar to a question we did earlier. Well, we know 5n over 18 is an integer. We also know this separately 3n over 18 is an integer. Well, the second one tells us that n over 6 is an integer, which tells us basically we don't know if there's enough information. We don't know, there could be we could be missing a 3 now because one of the factors is cancelled. So this one alone won't be enough. Whereas 5n over 18, there's no cancelling to be had here. So this must be 5 times n over 18. That makes sense. And that must be an integer. And so therefore, if n over 18 is an integer. So 1 alone is enough, but 2 alone is not. If x is an integer, is x squared plus 1 an even number? Okay. So x is an odd number. Well, then using our notation, we can say x squared. Well, if x is an odd number, we can say x equals 1. So we've got 1 squared plus 1 times 1 plus 5, which is 6. In other words, 2 times 6, which is 12, which reduces down to 0, which equals even. And so that is even. So 1 is enough. Each prime factor of x squared is greater than 7. So the prime factors of x squared are the same as the prime factors of x. So prime factors of x all greater than 7, e.g. we don't have a 2, no 2s, e.g. x equals odd. And so that's actually the same statement again. So that alone is enough as well. If x, y, and z are integers and xy plus z is odd, okay, so we can say xy plus z equals 1. Is x even? Okay, so 1, we've got x brackets y plus z is even, so we can say that's equal to 0. And so either x equals 0 or y plus z equals 0. In which case, well, in the first case, clearly x is even. Or if y plus z is 0, well, in other words, this one translates into y equals 0, z equals 0, or y equals 1, z equals 1, remembering that we sort of reset every time we reach an even number. So if y equals 0 and z equals 0, well, then we get a contradiction here, because we get 0 plus 0 equals 1. So that can't be possible. Whereas if y equals 1 and z equals 1, then we've got x plus 1 equals 1. In other words, x equals 0. So actually, that alone is enough. Whereas number 2, y plus xz is odd. So that tells us that y plus xz equals 1. I mean, it's just not, that alone is not enough to tell us what whether x is 0. We've got that and the other one, but we can't eliminate anything really from that. I suppose what I'd try doing is adding them together. So we get x, y plus z plus y plus z. Ooh, we could get somewhere, equals 2. So in other words, equals 0. So rearranging that, we get x brackets y, x plus 1 lots of y plus z equals 0. So that statement tells us either x is odd, e.g. 1, or y plus z equals 0. And so that's actually not enough. Well, actually, wait, x is odd. So that's told us whether x is an even integer, or y plus z equals 0, in which case, as we know before, so then it reduced down to the same things before. X is odd, or we go back to this case, which leads us to x is even. So in other words, we don't actually know. Tricky second bit. We nearly got there, but we ended up saying that either x is odd or x is even. So, okay. Club X has more than 10, but fewer than 40 members. Okay, so the members we'll say is n. 10 is less than n is less than 40. That's always nice. Sometimes the members sit at tables with 3 members at one table and 4 members at each of the other tables. Okay, so what has that told us? Well, it's told us that n equals a bunch of 4s plus 3 left over. And then it's also told us they sit at tables with 3 members, so a bunch of 3s, a bunch of 5s with 3 left over. And then the question is, if they sit at tables with 6 members at each table, plus some amount at the other one, how many will be left? So effectively, we need to find n. Well, okay, it's just a multiple of 5 plus 3. So what could n be? 13, 18, 23, 28, 33, 38, and it's a multiple of 4 plus 3. 15, 19, 23, let's just check if there's any other ones, 27, 31, 35, and 39. So the only thing it could be is 23, in which case, how many are left over when there's, we divide that into 6, 5. For every positive integer n, the function hn is defined to be the product of all even integers from 2 to n inclusive. Okay, so in other words, it's 2 times 4 times times n, and it's all of the even integers, which I can factorize out n. Effectively, I can factorize out a 2 from every single number. How many of them? I suppose it's 2 to the n over 2 of them. I'm not too worried about that, because then that leaves us with 1 times 2 times ... all the way up to n over 2, which is 2 to the n over 2 times n over 2 factorial. Okay, if p is the smallest prime factor of h100 plus 1, well, so then h100 plus 1 equals 2 to the 50 times 50 factorial plus 1. then P is, okay, so in other words, we know this thing, the smallest, this has every single prime factor up to and including anything less than 50. And so if we add 1, it no longer has any of those prime factors. And so the answer is greater than 50, which is the same as greater than 40, or obviously not, but that's the answer. Okay, if 10 factorial, let's rewrite this. If 10 factorial minus 2 times 5 factorial squared, okay, is divisible by 10 to the n, what is the greatest value of n? Ooh, okay. So we want to ideally factorize this a little bit, or at least think about, well, okay. A little bit nasty, this question. So, but let's start making some progress. What can I do with this? But I'm thinking the minuses are really messing this up. So this is, let's factorize out a 5 factorial. This is 5 factorial times 6 times 7 times 8 times 9 times 10 minus 2. So in other words, 10, you'll see what I'm writing, 10 times 4 times 3 times 2. That second bit being the 5 factorial left in there. Okay. And so then what are we talking about when we talk about it's divisible by 10 to the n? Well, it's effectively how many 5s are left. And remember that minusing and adding sort of ruins everything. So that's why I'm really trying to actually get what's left when I've sort of factorized and I've only got products left. So then what else can I take out of this? Well, I can take out the 10, and I can replace this 4 and a 2 with 8. And then I can take out a 3 as well. So I can take out a 10 times 8 times 3, and just be left with, what have I got left? I've got 2 instead of 6 times 7 times, well, we've got rid of the 8, we've got rid of the 10, so 2 times 7 times 9 minus 1. Okay, that's going to be 97. So 97 doesn't, that's just 97. So that's not going to contribute any 2s or 5s. Well, yeah, because it's odd and it's not divisible by 5. So then all we're left with is this idea, 5 factorial times 10 times 8 times 3. Well, that's 5 times 4 times 3 times 2 times 10 times 8 times 3 times 97. What a nasty question. So how many 5s do we have? We've got, and do we have more 2s? How many 5s do we have? We have, I believe, only 2 5s. Is that correct? Looks like it. So we've only got 2 5s, and we've got more 2s than that. So the answer is actually 2, because we've only ended up with 2 5s, which maybe is surprising. But so just notice how careful I am the moment we sort of add subtraction in. It just ruins any rules you have for divisibility. So I had to get rid of any subtraction. Okay. If an integer c is randomly set from 20 to 99 inclusive, what is the probability that c cubed minus c is divisible by 12? Well, c cubed minus c, that is something you should get very familiar with. C squared minus 1, which is c minus 1, c plus 1. In other words, 3 consecutive integers. And so, and what's 12? 12 is 2 squared times 3. And so, well, actually, we don't have a problem with the 3, because in 3 consecutive integers, we're always going to have one of them being a multiple of 3. So the only question is, what's the probability we get a factor of 2 squared? Well, effectively, we can either have the first one being even, in which case this one will be even. So that happens. So C even half the time. Or if C is odd, which also happens half the time. Sorry, this still follows. Then, sorry. Let's just to make it clear. If C minus 1 is even, then C plus 1 is even. And if C minus 1 is odd, which also happens half the time, then we need C to be divisible by 4, which happens, you know, you pick a random, C is even in this case, you pick a random even number, that happens half the time that it's divisible by 4. So we've got another half there. And so the answer will be half plus half times a half, which is simply 3/4. And so that will be our answer, C. Okay, if n and y are positive integers and 450y equals n cubed, which the following must be an integer. Well, immediately looking at this, I'm just going to factorize that. So that's 2 times 225, which is 2 times 15 squared, which is 2 times 3 squared times 5 squared, times y equals n cubed. And because we know cubes must have factors of 3 on the left, in all the prime numbers must have multiples of 3 in their exponents. So we're missing some things in y. So what must be in y? As in y must have at least 2 squared in it, because we're missing 2 powers of 2, at least a 3 in it, and at least a 5 in it. And then, you know, some other numbers which we don't really care about. So in other words, y over certain numbers, which must be an integer, well, y over 3 times 2 squared times 5, that must be. But any of these other ones, they don't have to be, because they're not, we haven't got that out of y for sure. So the answer is 1 only. Okay, this, hopefully at this stage, you're noticing that this immediately shouts difference of 2 squares. So I'm just going to rewrite this as 3 to the 4 plus 2 to the 4 times 3 to the 4 minus 2 to the 4, which repeating difference of 2 squares, and then repeating it again, and then the last one. And so what actually is this? This is 1 times 5 times 13 times 81 plus 16, which is 97. 97 is potentially prime. Well, I think it's prime, but even if it's not. So which of these is not a factor? Well, 97 is, clearly. 65, well, that's 13 times 5. So that is 35. Well, that's 5 times 7. We don't have any 7s. And so 35 is the answer. Okay. How many positive integers less than 100 are neither multiples of 2 or 3? So, well, how many positive integers less than 100 are there? There are 99 positive integers less than 100. Is that right? Sounds right. Yeah. Okay, so we've got 99. And then we want to subtract off the multiples of 2 and the multiples of 3. But then sort of thinking about it, well, if we subtract off the multiples of 2, then we'll subtract off them. And we subtract off the multiples of 3, we'll subtract off them. But then we've sort of subtracted all the multiples of 6 twice. So we have to sort of add back on the multiples of 6. And this is called the inclusion-exclusion principle, and we'll cover it more in overlapping sets. But so now that we've done that, well, now we want to be very careful with the numbers because they've been very nasty and giving us off by 1 errors. So how many multiples of 2 are there less than 100? Well, sounds to me like there's either going to be 50 or 49. Let's just think about it. We start at 99, we end at 1. Ooh, that sounds to me like it's probably going to be 49, I believe. Let's just think about it. 2, 4, 6, 8, 10. So we've got up to 5 there. And then we're going to miss out the last one of 100. So yeah, 49. Okay, so 99 minus 49. Multiples of 3. 99. So I believe that's just going to be 33. 3, 6, 9, and then, yeah, 3 more, 33. And then multiples of 6. So 99 divided by 6. So we've got what? 6. So 60 is 10, 90 is 15, 96 is 16. So we have to add back on 16. And so that's got us to 17 plus 16, which is 33. Very, very easy to get that one wrong due to being off by 1. Then we've got the same question again, apparently, by mistake. Okay, if x, a, and b are positive integers such that when x is divided by a, the remainder is b. Okay, so in other words, x equals some amount of a, some as in a times some number plus a remainder of b, and it's also equal to some amount of b plus a remainder of a minus 2, which the following must be true. Well, okay, so what has that actually told us? Well, what can a remainder be? A remainder can only be between 1 and the number you're dividing by. So in other words, what has this actually told us? 1 is less than or equal to b is less than, no, not less than or equal to, is strictly less than a. But also 1 is less than or equal to a minus 2 is strictly less than b. And so having a look at this, well then, let's simplify this one. 3 is less than or equal to a is less than b plus 2. Okay. And so just having a look at this, well, okay, so on a number line, this is a bit of a weird question, but literally just think about it on a number line. We've got 3 here, and then a is somewhere here. If a is here, then we know that a is less than b plus 2. So we can put sort of, well, but also b is less than a. So b must be somewhere over here, but b plus 2 must be somewhere over here to the right of a. And they can't be, can they be the same number? No, we know they can't be the same number because they're remainders. And so that must mean that a is equal to b plus 1. There's only one number in between that a could be. And so that means b is equal to a minus 1. So it's D. Very nasty question, and all just about sort of translation and seeing what's going on. If x and y are positive integers, which of the following cannot be the greatest common divisor of 35x and 20y? Okay, so we're just immediately going to write down in prime factorization what's going on. So we've got 5 times 7x and 2 squared times 5y. And so the greatest common divisor at the moment, we know for sure it's at least 5. And then just because that's obviously the repeated factors. And then it's anything else that's shared by both x and y. So we can definitely have 5. We can have 5x minus y. I know that looks a bit weird, but for example, x minus y could be 1. There's no reason why it couldn't be, in which case this is just 5. So there's actually no problem with that. What about 20x? Well, in order to have 20x, we'd need to have we'd need to have a 4 in this row, as in we have to have a 4 there that's not part of x, and so in other words, we're missing a 4. So we definitely, because that's the only way we could have 20x, because there's only one way of taking out 4. So actually we can't have 20x, so that will be the answer. And then obviously 20y, that's fine, we've got that there, and 35x, that's fine because we've got that there. So that will be C. If x is the smallest positive integer that is not prime and not a factor of 50 factorial, what is the sum of the factors of x? Okay, wow. So nasty looking question. What's the smallest positive integer that's not prime and not a factor of 50 factorial? Okay, so 50 factorial definitely has all the numbers from 1 to 50. So the first thing that's not a factor will definitely be above 50. The next, and the first thing that isn't a factor will be the first prime above 50 factorial. So 51 isn't prime, but 53 is prime. So we can say 53 is not a factor. But then we need to actually find the smallest integer that's not prime and not a factor. So the best we can do then is say, well, the smallest one that's not prime and not a factor, well, it must contain 53, because otherwise it's just prime factors, which are all in 50 factorial. So if we just double 53, as in times 53 by 2, it's no longer prime, but it is also not a factor. And that's about as small as we can get. And so what is the sum of the factors of x? So x equals 106. And so the sum of the factors, well, it's 106 plus 53 plus 2 plus 1, which, just looking at these answers, it's obviously going to be 162. Nasty question there. N is a positive integer, and k is the product of all integers from 1 to n inclusive. Okay, so it's n factorial. If k is a multiple of 1440, okay, well, first of all, we need to say that k equals 1440, which is, that's going to be 2 times 5, so 10, times 12 squared, which is, 12 is 2 squared times 3, so 12 squared is going to be 2 to the 4 times 3 squared. In other words, we've got 2 to the 5 times 3 squared times 5. And so we need to make sure that we have at least 5 2s, 2 3s, and a 5 in n factorial. So if we have, well, it looks to me like 8 will probably work, 8 factorial, because we've got, that's just to explain this reasoning. Okay, well, we've got our 5 that we need. We've got our 2 3s that we need. We've got one there and one hiding in 6. We've got our 5 2s. We've got 3 there and 2 more there, and, easily enough. So 8 factorial works. So we can say that the answer is A. When 24 is divided by the positive integer n, the remainder is 4. So we can say that 24 is equal to some amount of n plus 4. And so, therefore, just rearranging that, 20 equals Qn. And so, which of the following statements about n must be true? N is even. Well, to be honest, this is, we've only got a few cases. So we should check the cases for what's possible, because n is, so n must be bigger than 4. We know that because it's got a remainder of 4. So let's just check the various possibilities. If n is 5, then oh, sorry, just quickly, 20 is 2 squared times 5. And so our options for n are simply, it has to be we must have the same prime factors on the left and the right. So in other words, n can only contain 2s or 5s. So n could be 5, n could equal 10, or n could equal, I believe, 20. And so those are only options. And so n doesn't have to be even, but n is a multiple of 5, and n is also a factor of 20. So 2 and 3 only. If n is a non-negative integer such that 12 to the n is a divisor of that horrible number, except you can just immediately notice that the last number, the last digit, is odd, and 12 to the n is even. So in other words, for that to be a divisor, we just need this. This is almost a trick question. We need this to be 12 to the 0 because that's equal to 1. That's the only way we're going to get an even number being. That's the only time 12 to the n isn't even. And so we know n is 0. And so then the question is, what is the value of 0 to the 12 minus 12 to the 0? In other words, literally just 0 minus 1. So the answer is B. A bit of a trick question there. How many integers between 1 and 16 inclusive have exactly 3 different positive integer factors? So number of factors of a number, n, in prime factorization is p1. If it's p1 to the x, p2 to the y, etc., it's just going to be x plus 1 times y plus 1, etc. And so in order for this to be 3, well, 3 is a prime. And so we must only have one prime, p1, be our only option. And so we must have something to the 2 as our number. So in other words, 1 doesn't work, but 2, we could have n equals 2 squared. That will work. N equals 3 squared. That will work. And not n equals 4 squared, because that's actually in prime factorization, that's 2 to the 4. And so that looks like those are only options, because then we're above 16. So the answer is 2. Okay, the greatest common factor of 16 and the positive integer n is 4. Okay, so let's just write this out. 16 equals 2 to the 4, and n equals something. And we know that the greatest common factor is 4, so we know that n definitely has at least 2 squared in it, and no other 2s. The greatest common factor of n and 45 is 3. So in other words, 45 is 3 squared times 5. So n also must have exactly 1 3, but no 5s. Which of the following could be the greatest common factor of n in 210? So let's just write out what 210 is. That's going to be 3 times 70, which is 3 times 2 times 5 times 7. Okay, and we know that so we know that n definitely contains this, and no 5. It could contain a 7. So the answer for the greatest common factor, well, we've definitely got a 2, we've definitely got a 3, we definitely don't have a 5, and then we could have a 7. So it could be 6 or 42. And so the only one that could be the answer is D. If p cubed is divisible by 80, okay, so p cubed equals 80 lots of something. So 80 is 2 to the 4 times 5 times, let's say, something else, m. And we know for cube numbers, they're always multiples. The prime factorization has multiples of 3. So what must be an m? We must have at least p cubed equals 2 to the 6 times 5 cubed. That's sort of as small as we could make it. And so p must be at least 2 squared times 5. And so how many distinct factors does that have? Well, it's got 2 plus 1 times 1 plus 1. In other words, 6. So it must have at least 6. A and B are positive integers such that A over B equals 2.86. Well, that's a bit useless in terms of divisibility. So I'm just immediately going to rewrite this as 100A over B equals 286. And now we can start sort of thinking about divisibility rules. So let's start prime factorizing. 100 is 2 squared times 5 squared. A over B equals 286, which is 2 times 143, which sounds like it might be prime. No, it's not. It's 2 times 13 times 11, so 2 times 11 times 13. Okay. Which of the following must be a divisor of A? And so now we can rearrange this because we're trying to find, we know that B is an integer, so let's rearrange for B. We've got that B is equal to 5 squared times 2 times A over 11 times 13. And since B is an integer, both 11 and 13 must be a divisor of A, and so 13 is. And so the answer is B. Okay, and that's all of the questions. So hopefully that is helpful and shows you how to approach these sort of questions.